In this video, we're going to talk about the notion of an ideal of a ring. So here's a definition. So let's let R be a ring. And from now on in the videos, whenever I say ring, I'm always going to mean a commutative ring with unity, unless there's a really good reason to assume otherwise. And that actually is possible. For example, in this video, we're going to talk about ideals. An ideal is a subring of a ring with special properties, and that subring may or may not have the identity in it. So that's one example of a case where we might talk about a subring that doesn't have unity. But usually what we will start from will be a commutative ring with unity. Okay, so anyway, definition. Let R be a ring. We say a subset I of R is an ideal of R if the following two things are true. Number one, I is an additive subgroup of R. So remember that R being a ring has to be a group under addition, so we're saying I has to be an additive subgroup. And second, if X belongs to I, and R is any element of the ring, then Rx also belongs to I. So in other words, we say I absorbs multiplication. And that's the definition. Now, one thing I should mention, even though we're going to work mostly with commutative rings in this course, is that if R were a non-commutative ring, we could define what it means for I to be a left ideal or a right ideal, and that would depend on whether I absorbs multiplication on the left or on the right, or possibly both. But here we're going to talk about commutative rings. So if this condition 2 here is satisfied, that is, X being in the ideal and R being any ring element implies Rx is also in the ideal. If that's true, then XR would also be in the ideal. So this subset is going to absorb multiplication both on the left and on the right. Now, the reason we care to work with ideals, that's something we're going to get into in a later video. It has to do with the fact that ideals are perfect for constructing quotient structures, and that's a whole nother video. But in this video, I want to give a couple of examples of ideals of various rings. So here's a first example. We'll call this example 1. All right, let's let our ring be the ring of integers, standard operations, and let's define I to be the set of all x in the integers such that x is even. Okay, and I'm going to show that I is an ideal of R. Okay, the way that we do that is we verify that I has these two properties. Number one, it's an additive subgroup, and number two, it absorbs multiplication. So let's see if we can prove that. So first of all, if x and y both belong to I, then x and y are both even. Okay, so x plus y is also even. So x plus y also belongs to this subset. Okay, so my subset's closed under multiplication. We know 0 belongs to I because 0 is even. And if x is even, that is, if x belongs to I, then x is even. And so the opposite of x is also even. So opposite of x also belongs to I. Okay, now I probably could have done that more efficiently. I probably could have done like a one-step subgroup test, but that's a little more thorough here. So I've proven that I is closed under addition. It contains the identity. It contains the inverse of each of its elements. So I is a subgroup. Under addition, of course. Okay, great. What about number 2? What about absorption of multiplication? Well, let's suppose x belongs to I, and R is any element of my ring, so any element of the integers. Okay, well then x is again even, So r times x is also even. Now why is that true? Well, that's true because r is either even or odd. And we know even times even is even, and odd times even is also even. Now you could actually go a little bit more technical with this. You could say because x is even, x is divisible by 2, so x has to be expressible as 2 times some integer. And then you would see when multiplying r times x that r times x is it's still going to contain that factor of 2. So I'm being a little bit informal here by saying even times even, odd times even, but I'm just outlining a proof here. Okay, so anyway, so Rx also belongs to I, and thus I absorbs multiplication. Great. And by these two properties combined, I can say therefore I is an ideal of the integers. It's far from the only one. There are others we could come up with. We'll see a much broader and quicker method for coming up with a lot of ideals of a ring pretty soon. All right, so that's one example. Here's another one. And this one's a little bit stranger for reasons we'll talk about later. So let's let R be the ring of polynomials with integer coefficients. Okay, so again, z bracket x represents the ring of polynomials whose coefficients are integers. And I is going to be the set of all polynomials of the form a0 plus a1x, etc., up to am x to the m, such that all of the a's are integers. There we go. And a0, the constant coefficient, is even. This is a special example. Again, I'm not going to say exactly what makes this a distinctive example until a little bit later. But believe me when I say this is actually a rather important example in ring theory. Okay, for now we're just going to prove it's an ideal. All right, so to prove I is an ideal. Now again, just take note of the fact that the only thing that distinguishes elements of I is that this coefficient has to be even. So you could think of I as containing practically half of the polynomials in this ring, the half where the constant coefficient is even, and then there's also the ones where the constant coefficient is odd. Those are not in the ideal. All right, so we need to prove this is an additive subgroup, and it is also, it absorbs multiplication. All right, so number one, if I have two polynomials, a0, etc., up to am x to the m, and b0, and I want to be careful I don't require this to have the same degree, just by the way I write it down. So I'm using different variables for the degree of the first polynomial and the degree of the second. But if these are in I, then a0 and b0 both have to be even. That's the definition of these being in the in this set I. So the sum of these well, the way we define the sum is by collecting like terms, and the constant term of this polynomial, the sum, is just going to be a0 plus b0, and I could keep going. This is it's going to go all the way up to ak plus bk x to the k, where k is the max of m and n. But the really salient point here is that this is an even plus an even. That's an even number. Okay, so that means that this sum has to belong to I. And I'm being kind of fast and loose with notation here because I'm trying to get through this a little bit quickly. All right, so that means that my set is closed under addition. We can also prove that 0 belongs to the set because the 0 polynomial, sorry about that, that's a 0 there, since its constant term is 0, which is even. And also, if I write down some polynomial that's in I, well then, the opposite of that, we know what its constant term is going to be. It's just negative a0 plus negative a1x, etc. up to negative am x to the m. And that constant term still even, because a naught was even. Okay, so that was a lot of work to show, trying to convince you once and for all that I is at least an additive subgroup of R. But what about absorption of multiplication? So number 2, if this polynomial, really probably a better practice now that I'm thinking about would be to give these names, like call this P of x. So if that's an I, and Q of x, and I'm going to let this be anything because I have to prove that I can multiply an element of the subset by any element of the ring, not just something in the subset, and the product will still be in the subset. Okay, so this being in I means that a naught is even. Well then P of x times Q of x, it's going to be a mess. It's going to be kind of hard to write down exactly what the entire product is. But I will go ahead and write down at least this so that we can see that we are multiplying these things together. All right. And rather than get into a whole lot of trouble trying to work out exactly what this is, like what all the terms look like, remember, I just need to pay attention to the constant term to figure out whether this belongs to I. So the constant term of P of x, Q of x, what is that? I mean, how many ways are there to multiply a term of this times a term of this and get a constant with no variable in it? Well, I can multiply a naught by b naught, and that's pretty much the only way. Any other combination of terms is going to include at least one factor of x. So that constant term is just a naught b naught. And because a naught is even, the product is even. So that means that this set I absorbs multiplication. Therefore, let me write one more thing here. So P of x, Q of x belongs to I. There. Now I feel a little bit better saying, therefore, I is an ideal of z adjoint x. So those are a couple of examples, and there are other ones we could come up with, but hopefully this gives a sense of how to prove that a subset of a ring is an ideal.